All of you have done dynamics with me today. Now we're moving on to almost all of you. Okay, so sort of following the same basic structure, we're going to start with mathematical preliminaries, but it's a totally different set of mathematical preliminaries. So we're going to start in this class with matrices. Matrices with a C, and that's plural of matrix. So even if you don't remember how to do this stuff, you can sound smart when you talk about it. It is important, surprisingly important, depressingly important. Okay, so yes. Let's say we have a matrix 2, 1, negative 2, 4, 0, 6. This is a 3 by 2 matrix where the first number refers to the number of rows and the second number refers to the number of columns, always. And when you're talking about the individual elements of a matrix, you can talk about it as usually the matrix will be given an uppercase name and the individual elements will be lowercase. So like A1, 1 is equal to 2. A1, 2 is equal to 1. So what would that negative 2 be? What are the indices of that? Yep, that's 2, 1 is negative 2. 2, 2 is 4. A 3, 1 is 0. And a 3, 2 is 6. In this class, there are pretty much three different matrix sizes. The first one is 3 by 1. So does that have, is that skinny and tall or short and fat? Yeah, skinny and tall. So this is how we're going to represent vectors in 3D. For example, you could have a force vector of 10,000, negative 15,000, 1,000 with units of newtons. We'll talk about this sort of steadily through this class, but this is sort of a first glimpse at it. Any collection of numbers in a format like this is a matrix, but any 3 by 1 matrix is not necessarily a vector. And same thing with what I'm going to talk about is tensors. Like you can organize any numbers into a 3 by 3 matrix. It's a matrix no matter what those numbers represent. But that doesn't mean that it's a tensor. Vectors and tensors are sort of have kind of similar properties. And what those properties that property that they share is that those are measurable values where if you measure them in a different coordinate system, you get the same answers except for you need to apply a rotation matrix. Okay, we'll talk about rotation matrices and everything, but if you, so with vectors, you're used to this idea. You know, if I push down on the table, the force vector I'm applying to the table is like this, right? And if you use a coordinate system like this to measure that vector, you get one thing. If you use a coordinate system like this, you get another thing. But they're related in the sense that if you choose the right rotation matrix and multiply it to the vector in one, you get the other one. Tensors have sort of a similar property, and that's going to be one of the things that we're going to deal with quite a bit. So for now, a matrix in general is not a vector or a tensor. It has to do with what you're measuring. And there needs to be this sort of this consistency between the measurements you take in different coordinate systems. Okay, second type, so that's a vector. The second type of matrix that we're going to see a lot is 6 by 1. And we're going to see this as what's called the voicestress and also the voicestrain. So for example, the void strain could be 1.5 times 10 to the minus 5, 0, 0, negative 6 times 10 to the minus 6, 1, 2, 3, 4, negative 1 times 10 to the minus 6, 0. This is the void. This would be a void strain, and strain we haven't talked about it yet, but we'll see that it has no units. It's just a set of numbers. It's unitless. How many did I say? 4. There are 4 types of matrices. Sorry about that. The third type is a 3 by 3 matrix, and this is the format that we'll use for the stress tensor. And also for rotation matrices. So for example, a stress tensor might look like this: 6 times 10 to the 6, 0, negative 8 times 10 to the 7, 0, 5 times 10 to the 7, negative 2 times 10 to the 6, negative 8 times 10 to the 7, negative 2 times 10 to the 6, negative 5 times 10 to the 7. And the units, the SI units for stress are pascals. One thing you might as well sort of start noticing now is look at this symmetry that we have in this case for the stress tensor. There's no relationship between the 3 diagonal elements. Those can be anything. But if you show the mirror image of the off diagonal elements about that diagonal, they all have to match. This and this are the same. This and this are the same. This and this are the same. And that's a requirement for the stress tensor. It's called a symmetric matrix. Yes? Sigma, yep. Epsilon, that's right. Oh, yes, that is the symbol for a matrix. In textbooks and stuff, you usually see matrices just given as a, like in a bold font. But I don't have a bold when I write, so under squiggle is what people usually do. That's what I don't know what it's really called, but I call it under squiggle. I like the way it sounds. And then the fourth type, the last type that we're going to see all the time, is 6 by 6. And that's the stiffness matrix. And also the compliance matrix. I'm not going to do examples of those because it would just be me writing 36 values. Oh, one more thing that I want you to start noticing now about the stress and the strain. Okay, so I represented the stress in the tensor form. I represented the strain in the Voigt form. But, well, there's sort of two things, I guess, to notice. The Voigt strain has 6 independent values. How many independent values does the stress tensor have? 3 on the diagonal, but then also 3 off diagonal, and then the other ones have to repeat it. So both of these two forms show 6 independent values. You can sort of imagine why it might be useful sometimes to represent the stress tensor just as a list of 6 values. And then second, I mentioned last class that strain is a measure of deformation at a point, how much the thing is stretched and twisted and compressed at a single point. So that's deformation. This is a measure of load at a point. And we'll talk about, what those mean and stuff, but basically just think of this as deformation and load. And if we're talking about, I said that deform is the most important materials that we're dealing with in deform are metals, steel or whatever. If you're talking about the deformation of steel under load, you're going to be talking about very large loads to produce a very small deformation. Okay, and so in any real example where we're using real material properties, you should get things way, way bigger than 1 for the stresses and way, way smaller than 1 for the strains. Okay, so if you ever don't see that in a real example, you want to, at the very least, check your work carefully, Oh, similarly, we don't know how to define these yet, but a stiffness is a measure, stiffness values are bigger if the material is very stiff. Compliance matrix values are big if the material is very compliant. In the overall scheme of things, steel and iron and copper and whatever are pretty stiff. So generally, the elements of the stiffness matrix are going to be really big. The elements of the compliance matrix are going to be really small. Again, like way, way bigger than 1 and way, way less than 1. Okay, turning matrices into your calculator. So I'll just say for TI calculators, if anybody has a different brand of calculator, we can look at it and I'll scratch my head and tell you I don't know after we stand there awkwardly for 15 minutes. Okay, so in the TI calculators, there are three ways that I know of to enter values. The way that you have to use, I think on the TI 83 and the TI 86 maybe, is you have to go to the matrix, hit the matrix button, and then there's a place, a heading that says edit, and you go into edit, and then it asks you how many rows, how many columns, enter those, and then plug in the values. That's a more tedious way. It's just a real clicky way. Click, click, click. The other two ways, if your calculator does it, I think you'll find are faster, but any of these work fine. So the second way is to do it with square brackets, where you have first square brackets defining the matrix, and then inside the first square brackets, you have other ones defining the rows. So, and then commas separating the different values. So, like bracket, bracket, 2, 1, close bracket, and then open bracket, -2, 4, close bracket, and then new bracket, 0, 6, bracket to end the row, bracket to end the matrix. And then you can use the store button to put that into, some variable, whatever it is, A. If you do that, you should get the matrix back out that I gave at the start of this. And if you do this, it also should print out on your screen the matrix in matrix form, so it's easy to figure out whether you did it right. And then the last way, I think this works on 84s and 89s, and I think 89 is the only one that accepts this, but it's a few less keystrokes, just a square bracket to define the matrix, and then commas to go across the row, and then semicolons to go to the next row. So it would be like 2, 1, semicolon, -2, 4, semicolon, 0, 6, and then bracket. If you can't figure it out on your calculator, we can probably figure it out together. Okay, so next we have to talk about the matrix operations that are going to come up a lot. The first one is transpose. Every matrix has a transpose. And you get it by replacing every I, J element with the J, I element. What you're basically doing is turning what used to be the rows, you're turning those into columns, and vice versa. So the old rows are the new columns. So for example, if your matrix A is, I'll use that same one again, 1, 2, oh no, this is not the same one. 1, 2 is the first row, 3, 4 is the second one, 5, 6 is the third one. And the transpose, you call it A transpose with a capital T looking like an exponent, is equal to, so in the first case, 1, 2 was the first row. Now that's going to be the first column. 1, 2. 3, 4 was the second row. Now that's going to be the second column. 5, 6 was the third row. Now that's going to be the third column. And I think at least the 89s and the 84s have a transpose function. I think the 83s and 86s do too. But if yours doesn't, it's easy to write a program that does it. And I would recommend doing that because we're going to use a lot of transposes. But here's what I was saying about the ij and ji element. Okay, so this 3 here in the original matrix, what element is that? What number? 2, 1, right? It's in the second row, first column. Over here, it's in the first row, second column. So 2, 1 in this case, 1, 2 in that case. Okay, you're always just flipping the indices. Okay, so every matrix has transpose, but a lot of the things that we're going to use are only applicable for square matrices. That's going to be the most important thing for us. So I have to define a square matrix. And if you had to guess what for $1 million, guess what a square matrix is, it would be exactly what you think it is. It's the same number of rows and columns. I don't have $1 million to give you that. So it has the same number of rows and columns, which means when you write it out, it looks like a square. So for example, 1, 3, 1, 2, 2, 4, 1, 0, -6 is a square matrix. And every square matrix has what are called diagonal elements. And those are the ones where the row number is the same as the column number. I'll write it as I equals j. So the only ones where I is equal to j in this example are, here's the 1, 1 element, the 2, 2 element, and the 3, 3 element. So these are the diagonal elements for this example. So we're going to deal with square matrices. We're basically two types of matrices, either what are called column matrices, those are the 3x1 and the 6x1, or else square matrices. We're not going to really use any other kind. So we're also going to most often use a special class of square matrices, special type of square matrices that are called symmetric. That's the type that I pointed out when I gave that example stress tensor. So a symmetric matrix has to be square. And the requirement for a symmetric matrix, so let's say for a symmetric matrix A, the matrix A has to be equal to its own transpose. Okay, so for example, 1, 2, 6, 2, -9, 4, 6, 4, 0. That's a symmetric matrix. And so let's think about how that relates to this requirement that the matrix is its own transpose. The matrix A is, the first row is 1, 2, 6. The matrix A transpose, its first column is 1, 2, 6. Okay? The matrix A, its first row is 2, -9, 4. A transpose, its first column is 2, -9, 4, and so on. So if you take the transpose, you get the same thing back. There are two important properties of symmetric matrices. The first one is, well, let's just talk about 3x3. So a 3x3 symmetric matrix. How many total elements are there in a 3x3 matrix? 9, but a 3x3 symmetric matrix only has 6 independent values. So if you're given those 6 values, you can fill out the rest of the matrix. You can think of these as the ones sort of making the upper triangle. You can think of those as the independent ones, and you could fill in the ones that aren't circled there based on those. And the second thing that's important, it's not going to come up until quite a bit later, but symmetric matrices have only real eigenvalues. So they always have exclusively real eigenvalues. And I think it's fair to say that it's usually the case, it definitely is the case in this class, that when you're dealing with symmetric matrices, there's a useful, very physical meaning to the eigenvalues. The fact that those eigenvalues are real sort of comes about because there's a physical meaning to what those eigenvalues are, and we'll see that's the case in this class. In general, you can calculate eigenvalues of any 3x3 matrix or any square matrix, but in general they're going to be complex, but not if the matrix is symmetric. Okay, so now let's talk about some calculations that we're going to do with matrices. The first one is matrix multiplication. And for the most part in this class, there's not really any reason that you have to know. I mean, there's a couple of questions that I'll ask here and there that'll require that you understand how matrix multiplication works. But in almost every problem you do in this class, you're just going to plug the matrix into your calculator. And so, who cares how it works? You can learn about that in the math department, But you can think of matrix multiplication as a series of dot products. Between rows of the left matrix and columns of the right matrix. The dot product works like this. If you have a vector 2, 1, -2, and you take the dot product with a vector -5, 0, +6, that's equal to 2 times -5 plus 1 times 0 plus -2 times 6. So that's -10 plus 0 plus -12 or -22. So notice that the output of a dot product, even though you're inputting two vectors, the output is always a scalar. And that's why people a lot of times call that the scalar product also. So the way it works for matrices is, so let me just sort of demonstrate how this works. So if your matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're multiplying it by 10, 11, 12, 13, 14, 15, 16, 17, 18. Then the output is going to be a matrix. And the way you calculate it is dot product between row 1 and column 1 gives you the 1, 1 element. And if you take the dot product of 1, 2, 3 with 10, 13, 16, you get, I believe, 84. Then for the 1, 2 element, we're going to take the dot product of the first row with the second column. Dot product of 1, 2, 3 with 11, 14, 17. And for that one, I think you get 90. Then for the 1, 3 element of the output, what row are we going to multiply in the first matrix? First, yep. That's where the 1 comes from. And what column in the second matrix? Yep. And so dot product between these two, what I have written down here says 96. Now we go to the second row of the output matrix. To get the 2, 1 element of the output matrix, what row do you think we'll use second? Yep, second row, first column. And that product gives you 201, according to my paper, which, as far as I know, was written by some crazy person who lived in our neighborhood. And for the 2, 2 element, we'd multiply second row, second column. And I have 216 for that one. For the 2, 3 element, it would be third row. Oh, yes. Thank you. It's still on the, so we're still on the second row, and now the third column. And the dot product of those two gives 231. And now we're on the third row of the output. So we're going to be using the third row of the first matrix the whole time. So we'll start with this dot product with the first column of the second matrix. And I think you get 318. At least that's what that guy in my neighborhood thinks. The second one, we're going to have third row, second column, and that dot product gives 342. And then the last one is third row of the first matrix, third column of the second matrix. What? Oh. Yeah, let me know if you do any of these and these numbers are wrong. And then that gives 366. But if you just enter into your matrix, in your calculator, the matrix 1, 2, 3, blah, 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 and in a different variable, you put in 10, 11, 12, blah, 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 and then you just use the multiplication symbol between those two, it'll spit that out much faster than doing it yourself. So, for example, in a TI 89, you could write this as 1, 2, 3, semicolon, 4, 5, 6, semicolon, 7, 8, 9, close bracket, times The second matrix is 10, comma, 11, comma, 12, semicolon. 13, comma, 14, comma, 15, semicolon. 16, comma, 17, comma, 18, close, and it'll give you this answer. Okay, so here's a question. Can you multiply any two matrices? Let me write the question first. And the answer is no. What are the requirements so that you can multiply two matrices? That's right. The first matrix has the same number of columns, elements in the rows, as the second matrix has rows, which is the number of elements in the column. So the number of columns in matrix 1 is equal to the number of rows in matrix 2. And so if you're multiplying, well, I say matrix 1 and 2. Matrix 1 is the left matrix, and matrix 2 is the right matrix. So if your left matrix is M by I, so you have M rows in your left matrix and I columns, and your right matrix is N, nope, is I by N, then if you multiply those, what are going to be the dimensions of your output matrix? Yep, M by N. If you're dealing with square matrices, you don't have to think about all this too much, because you have everything is I. So your left matrix is like 3 by 3. Your right is 3 by 3. You multiply them and you get a 3 by 3. But we are a lot of times going to multiply a 3 by 3 matrix times a column matrix, like a 3 by 1 matrix. And so then your output is going to be 3 by 1. Here are a couple of important facts about multiplying matrices. So notice, the first thing is that the order matters in matrix multiplication. The matrix A times B is not equal to the matrix B times A. And if you're not talking about square matrices, there's not even any guarantee that you might be able to multiply them in one order and not even be able to multiply them in the other order. The second important thing to keep in mind is that if you're multiplying more than two matrices, The way that you group them in multiplying does not matter. So, for example, if you're multiplying A times B times C, you can do that calculation by first multiplying A and B, then multiplying the result times C. Or you can do it as A times the quantity B times C, and those give you the same answer. Any questions about that? You can think of matrix multiplication in terms of summation. This is useful if you ever need to write a computer program that does matrix multiplication. So the summation notation for matrix multiplication, that's a lot of shuns. Says if you're multiplying the matrices A and B, do the sum, I equals 1 to some constant value I of A M I times B I N. And that gives you the element A B M N. You won't need that in this class, but writing a program that does matrix multiplication is pretty easy. And if you're doing this kind of stuff, then whenever you go to a new programming environment, you need to write a function that does this, and that's how you do it. It's a one-line function. Okay, let me do one more thing, and then we can start with stress tensors next time. So the last thing I want to define is an inverse matrix. Most of your calculators have this function built in, so you don't have to know how to calculate inverses. And if it doesn't, then you should program it in. You don't want to be doing it, trying to do it each time. Every square matrix, no, that's not true. Only square matrices have inverses, inverse matrices. But not all square matrices do. And later, when we talk about eigenvalues, the requirements for a matrix to be invertible are going to be a big part of deriving the eigenvalue thing. But if a matrix A has an inverse, then A times its inverse matrix is equal to the inverse matrix times A. Remember that order matters in matrix multiplication, but in this specific case, it doesn't. And those are equal to what's called the identity matrix, where the identity matrix is 1, 0, 0, dot, 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 0, 0, dot, 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 with ones down that diagonal and zeros everywhere else. So that's called the identity matrix. Anyone know why that's called the identity matrix? Yep. That's right. Or you can multiply it by anything you're allowed to multiply it by, and you get the same thing back. So you can multiply this by vectors, column matrices, and you'll get that column matrix back. So so in a way, I mean, it works the same way that like a multiplicative inverse works. Like 3 times its inverse, 1/3, is equal to 1. And the thing with 1 is you can multiply 1 by anything else and it gives the thing back. That's the same thing that the inverse matrix does. Okay, that's it. Look, I probably won't be until tonight, but I'll put an assignment up for you for Friday.